Hi everybody, this is Mr. Zarzik, and in this screencast I'm going to talk about electric potential or voltage with a focus on equipotential lines or lines of equal voltage. If you haven't yet watched the video on equipotential lines with all the demos, I suggest that you pause this one and go watch that one and then come on back. In part one of the lecture on electric potential, we defined electric potential as the electrical potential energy per charge, where the way to think about it was to think about gravitational potential energy per mass, so that the mass part would just factor out and we'd be left with what's called the gravitational potential, or the product of G times H. Well, that's a good analog, and that voltage is really about just position within an electric field. And so this does a couple of things for us. First and foremost, it connects this concept of voltage to energy and to work. And then since we're specifically talking about potential energy, it gives us a way to think about it. All right, for the electric field, okay, we're interested in charge, whereas with the gravitational field, we're more interested in mass. When we talk about a charge moving through a change in voltage, well, it's really like saying it's in an electric field as opposed to a gravitational field, and it's changing its position within that electric field, relatively speaking. We've got to remember that this all just comes from opposites attract and like charges repel. Okay, everything is built upon those simple two rules, but what we've been able to do now is connect it to energy. And so if I take some positive charge and I move it from one position in the field to another, okay, we're really, the only direction that matters is the fact that we're now closer to this line of positive charges. Here we'd have to do some positive work on the positive charge to push it against the electric field. But see, the thing is that really all that matters is well, what's our height in the field here compared to what's our height in the field when we're finished? And that's what really matters when we talk about doing work. Okay, so just like if we talk about work to lift something, okay, well, the specific direction we talk about is lift it up, which is against the gravitational field, and that's going to tell you how much work you've done on a specific charge. Okay, so that's the analog. As we think about this voltage thing, it's just position within a field. And so if we understand what voltage we're at and what voltage we're going to wind up in, well, that's going to tell us about the work that gets done on the charge, which is going to tell us about its change in energy. And ultimately, that can tell us things like, hey, how fast will the charge be moving, or how much did it gain? And what's great about this is we can use this concept of voltage without actually knowing the specific charge that's involved. We control the space, and so any charge that we put in that space has to adhere to the rules that we set up. Specifically, it will obey the direction of the electric field. And so we introduced the idea of what's called an equipotential line. The term equipotential line just combines equal and potential. So electric potential is a line of voltage, and an equipotential line is a line where everywhere along that line you're at the same voltage. So I've set up a uniform electric field here with this line of positive charges, and so if I just draw a line like this, okay, remember our analog here is that voltage is like gravity times height. Okay, it's a position within the field, and so really these are all just positions where we're at the same location within the field. This is a line where anywhere along this line we're at the same voltage. If I were to draw another equipotential line, okay, like this, well, this is another line of voltage, and here's another one down here. So if I added in some positive charge here, okay, well, anywhere along this line it would be at some voltage, anywhere along this line it would be at some voltage, and anywhere along this line it would be at some voltage. If I moved it from here to here, it would undergo a change in voltage. The charge would undergo a change in voltage and hence some change in potential energy. But this is path independent, so how I go from here to here doesn't matter. See, so I could like move along anywhere I wanted. I could even go down here and then go loop to loop to loop to loop to loop. But if I ended anywhere along this line, I would undergo the same change in voltage as just going from here to here. So if I took this positive charge and I put it in the field and I let it go, it would get pushed upwards by the field. So we say that when a positive charge is released in a field, it moves from an area of high potential to an area of low potential. What that means is that the voltage over here is larger than the voltage over here. The closer you are to the source of the electric field, the beginnings of those lines, the higher the voltage you're at. Now, if I took a negative charge, okay, and I let it go in a field, well, then it'll be attracted to the positive, so the negative actually moves to a higher voltage or a higher electric potential if the field is allowed to do work on it. So that gives us an important distinction between electrical potential energy and electrical potential. Electrical potential, that's voltage, okay? So closer to the positive charge, that's a higher voltage. As we move along the field lines, we move this way, we're going to a lower voltage. The positive charge would have a larger electrical potential energy if it was down here close to these positive charges. The positive charge would be at a lower potential energy if it moved up here. So it's like the analog is if it was allowed to fall in the gravity field, the lower it was in terms of height, the lower the potential energy. So if we let the field push the positive charge, it goes to a lower potential energy as it goes to a lower voltage. The negative charge behaves just the opposite. Remember, opposites attract, so if I just let this negative charge go in the electric field, it would attract it towards these positive charges. It would naturally move towards the higher voltage, but in doing so, it would lose electrical potential energy. Remember, we have positive and negative charges, and the reason that we have this distinction of positive and negative is to indicate behavior. They behave just the opposite of one another. So to bring this back to electric potential lines, yes, it's true that we have a relationship for change in voltage in a uniform electric field in terms of distance, but the distance of separation, oftentimes we don't know it or we don't care. We can just look at this in terms of the change in voltage. So if I just kind of zoom in here, okay, I've assigned some values of positive 5 volts and negative 5 volts here just to kind of show a point, and that if I take and draw an equipotential line right in between, okay, well, I can determine the voltage really easy at this point, the midpoint in between negative 5 and positive 5. This would be a line of 0 volts. And if I drew another equipotential line right here, okay, well, now I'm halfway between 0 volts and positive 5 volts, so this would be positive 2.5 volts. And if I draw another equipotential line over here, midway between the 0 volt line and the negative 5 volt line, this is negative 2.5 volts. All right. With these uniform electric fields, we like it because it's really easy for us to map out the equipotential lines or the lines of uniform voltage. And something else too, it also demonstrates that, well, these lines that we're showing here for voltage, and I'm just going to make them solid just because it's going to be easier for you to see the point I'm trying to make. Okay, these lines of voltage, they're always perpendicular to the electric field lines. And that's an important property that allows us to make pictures from this to determine further meaning. In the Equipotential Lines tutorial, I showed you a whole bunch of demonstrations using a blanket to demonstrate what we call the topographic view. So picturing voltage as a view of mountains and valleys. Okay, so now I'm going to try to put some idealized diagrams to go with the demos that you saw. So if we start with just a positive charge, I've got these red lines going out to represent electric field. If you remember, electric field is just defined as what's the force experienced by some small positive test charge. And so if I took and I drew in a little positive test charge here, okay, no matter where I put it in reference to this collection of positive charge, it'll be repelled away. So it would get pushed this way or this way or this way. All right, well, our idea here is that at different locations along the field, it's going to be at different voltages. And that's what these little dash lines are here to show. These are called equipotential lines or lines of equal voltage. Okay, so this represents some voltage. This represents some voltage. This represents some voltage. And the closer we are to the positive, the higher the voltage. And so to go along with this idea, if this is our positive charge, okay, well then this slope that gets generated here is to represent the electric field. So if I put some little positive charge here, okay, along this slope and I let it go, it would move down the field. It would accelerate according to the slope, all right? Now with charges, we've got two varieties. So I do have positive and negative. If I took this negative charge, it would actually accelerate up towards the positive charge. It would actually accelerate uphill, which is a little funky to think about. If you're having a hard time visualizing it, well then just look at this part upside down and you'll be able to see it accelerating this way, which will make a little bit more sense. Now, the reason that we get this curve from the field comes from the fact that around some point charge, the electric field is calculated as KQ over r squared, where this charge here, this is the Q, and the magnitude of the electric field varies with r squared. So really this is like a plot of 1 over r squared just in all directions. These lines here represent my equipotential lines, or my lines of equal voltage. Okay, and the nice part about voltage is the drop-off just varies with the distance. So like if I double the distance, I get half the voltage. Triple it, I get 1/3. Quadruple 1/4, and so on and so forth. We'll take you through the derivation a little bit later on, but when we compute voltage around a point source, we get this K Q over R, where again, the charge here, that's the Q. This tutorial is not too much about equations and math, okay, so it's really just more about focusing on the concept. If I toss in a little charge here, well then anywhere along this line it would be at some voltage, anywhere over here it would be in a lower voltage anywhere along here, and so on and so on and so forth. What you need to remember is that these lines, these equipotential lines, okay, this little picture of like a tent with my little positive charge at the top, okay, the lines would go all the way around the tent. They'd make complete little circles all along this outer surface of this picture of the tent, which is really a representation of the electric field. Let me show you what I mean. We've seen groupings of charges, so I've got 2 positive charges, and there's some numerical values here because later on you're going to work this as a sample problem. Okay, but what does the electric field, and then more importantly, what do the equipotential lines look like around 2 equal positive charges? Well, sticking with this analogy of using a sheet or a tent or some kind of topography to represent, okay, well then the little positive charges would be like the peaks on this tent, or if you want to relate it back to the other video, like a blanket. Each one of these dashed lines is a line of equipotential. So it's like if we were up here and we took a walk around the tent, and we have to go all the way around. We have to go around to the back of the tent and then loop all the way around over here. Okay, as long as we maintain this height above the ground, we would be at this same voltage or same equipotential. All right, what's neat is if I go really up here close here to the 2 microcoulomb, I could make a little loop up here, okay, at some voltage. Well, I'd get the same voltage over here. These would be 2 independent loops. This point P is just right at the bottom of this tiny little valley, just right in between. Okay, so anywhere along here, I'd be at this exact voltage. At this spot here, it's kind of neat because this would be an equilibrium in that at this point, a little positive charge would be repelled away equally from this 2 microcoulomb and this 2 microcoulomb. Okay, but you see we're right along the edge here where we could fall off in either direction, so we call this an unstable equilibrium. And so this is a good opportunity to point out an important property of the equipotential line, and that is that they are continuous. They form closed loops, okay, so they go round and round and round and round. An electric field line will either start on a positive and then end on a negative, or that line can extend out to infinity. With an equipotential line, it forms a closed loop. It's always going to form one of these closed loops, and that loop will be perpendicular to the electric field. So if I look at this picture right here, okay, well, the blue lines between these 2 positive charges, these are electric field lines. And we've seen this picture before. These little red, it's kind of hard to see, but these little arrows that are showing the direction of the electric field. So it's like the electric field around a positive charge just radiates outward, all right, but that field is skewed and deflected by the fact that these 2 positive charges are repelling each other, and so literally their field lines repel one another too. If I look at what's in kind of a whitish, kind of gray color, okay, well, that right there, those are the lines of voltage. And so if I just pick one here, I'm just going to take this one. I'm just going to trace it out all the way around. Okay, and I'm going to try to be careful about this so that they don't accidentally jump. Okay, this forms one continuous loop. All these lines of voltage form continuous loops. If I'm far enough away, you see that the loop goes around both the positive charges, but if I get in close here, okay, well, you see that the loop actually just goes around this positive charge right here. So if you remember from the previous slide, okay, the peaks are little positive charges, so you can actually make little loops around them, but eventually you go out far enough to where you'd be moving around both loops on one complete path because you'd be maintaining this same elevation in the electric field. It's also worth pointing out that the voltage lines, the equipotential lines, and the electric field lines are perpendicular. So all these lines, as they cross, form right angles. Okay, every single one of these. So we could go on and on with these, and the voltage lines and the field lines are always perpendicular to one another. What about a positive charge and a negative charge? These two have equal magnitude, so this is a positive 2 microcoulomb, negative 2 microcoulomb. So we looked at the electric field between two charges with opposite signs but equal magnitude. Well, now what about the electric potential, or what about the voltage? Our picture would look something like this. Okay, so we'd have 1/10 that would go up above ground, and then we'd have a 1/10 that goes below ground. So this is like a peak, and this is like a valley. Now, something that's kind of neat that happens is out here, okay, the electric field follows that exponential decay. All right, same thing happens over here with the negative charge. But look at the space in between. The space in between the positive up here and the negative over here, it gets really flat. Okay, a flat electric field is a uniform electric field. And so just to add in the little charges, here's our 2 microcoulomb, here's our negative 2 microcoulomb. One way to think about this, since we're relating this to topography, would be like this is above sea level, this is below sea level, this is at sea level. Okay, and what's kind of important about this is if I took and I put a little positive charge in here, okay, and I let it go, it would move along the electric field. Just because it hit 0 volts over here, it wouldn't stop. It would move from the positive to the negative. If I looked at this from overhead, okay, well, this would be the peak of my mountain. This would be the bottom of my valley. Okay, the blue lines, those are the electric field. Okay, and you've seen this diagram before. The two fields attract one another. So around the positive charge, it radiates out. Around the negative charge, it radiates in. These should be straight lines if these are individual charges, but because they're not, okay, the fields attract one another. The lines of voltage are what are called contour lines sometimes. All right, those lines of voltage, okay, form those closed loops. So you can see the circle over here. Well, it's kind of an oval shape. But they form these closed loops. Okay, and then the voltage lines are perpendicular to the electric field at all points. Okay, and then just to show it, if we wanted to see that line of 0 volts, okay, let's see, let me get the right color here. I'm not really sure how to do that. So something like this. So that 0 voltage line would be right in between them right there. Okay, that midpoint. All right, so that brings us to the end of our screencast. Hopefully the demos and the diagrams and explanations are helping you make some sense of this thing that we call electric potential or voltage. From here on out, we're going to move on to calculation, which, believe it or not, is actually the easiest part of this. Or at least that's the theory. So thanks for watching. This has been Mr. Zardik saying I'll see you next time.